I just want to touch on translational symmetry. If, for example, let's consider the simple one-dimensional case, we have a function which we can consider to be finite function. Can I just, copy paste this function along the x-axis and create artificial symmetry, even if it's not there? Even if I have a discontinuous function, I can just recreate it, some kind of a ghost.
Yeah, so you're right. So what happens is, suppose you have a solitonic solution, so something that's concentrated, often called a sole solution. So you have your infinite line, and we have discretized it, and there is some bump someplace, and physically you think that might be a particle plus noise, or that might be a solution of some fancy nonlinear equation. Then the moment you put a box on this, you kind of violate this solution, because this solution only exists, even though it has very small exponentially Gaussian tails, it has them off to infinity. So then what you can do, you put a box, and that violates it a little bit. And then you run a computer program that makes sure that there is a nearby solution, which is actually periodic on a box, but it captures this solitonic thing. And, that's what you do. I mean, when you're trying to describe localized solutions. So what you do in quantum mechanics course, which is honest, they define a scattering problem. They define it, they say there are concentrated particles, little bumps here. There is a nucleus, and there is, another atom nearby. And what you do in scattering problems is you prepare an accelerator, so you have, thing that produces alpha particles, or God knows what, in the 19th century, 20th century, and you shoot it from infinity, of course. You're in meters, and this is an angstrom, so this is infinity to that accuracy, the 1 part in 10 to the 12 or something. You shoot it in, then it bounces around, and it shoots out. Now you can't put this on a computer because it's infinity to infinity. So what honest course will do is they'll put the system in a box, like we have done, hyperbox, 3 dimensions in this case. And they'll discretize that box. And they'll do calculation in that box. And then they'll show that once you've done the calculation, you can take a limit of infinitely many little steps, mathematical limit, not calculation, and you get a nice smooth function defined on the infinite. But when they put the box, they actually cover infinite space by repeats of a basic box. So when they put the box in, you have atoms here, but you have them in every box, every finite box, because they're periodic, so they have covered the space. So that's very unphysical. But you're looking only in one neighborhood, and that's called renormalization scaling. And you send the things off to infinity. Now, boxes are nice because everything is finite. Matrices are great. There are no infrared divergences. There are no ultraviolet divergences. So when you do this calculation, you control everything. And then you have to do a very careful thing on the finite size effect that says that when you take a correct limit, you get correct physics. But the real arguments very often are done like I'm doing them right now. You understand a finite box calculation. And it's really great. Finite box has, if on a line, if I have 7 sites, then I have 7, my state is described by 7 numbers, so field has values on 7 points. When I take this Fourier transforms I'm doing this week and next week, I get 7 Fourier components. And I'll show you, if I have time, that this is just, again, a matrix. I take my original thing, I bang it by a matrix, I get a Fourier transform. And, I can control both things. I can do calculations, go back and forth. And then I take the limit to large and to show that this is correct calculation up to the accuracy desired.